Good afternoon, everyone. So let's start our lecture today. Today's lecture is about PRNG, which is the abbreviation of pseudo-random generator. Today's outline has, I don't have an outline yet. So the first thing we're going to talk about is random number generator. Because we are talking about pseudo-random number generators, we have to know what random number generator is, or RNG. RNG is a device that is either computational or physical that is designed to generate a sequence of numbers that appear random. I think this definition is not very difficult to understand. So let me just tell you what kind of random number generators we have. Typically, we have two different types of random number generators. One is called true random number generators, or PRNG. And the other one is called pseudo-random number generator, which is the topic of today. Here I listed two types of random number generators in PRNG. The first one is called a lava lamp. This is a lava lamp. Do you know what lava lamp is? Yes, you know. Yeah. Lava lamp is used for decoration. So basically, it has three things in it. Water. Here, it has water. It has wax. And it has something called carbon tetrachloride. And this mixture has some colors in it. The special thing of this mixture is that when it's cool, it's more dense than water. So it will stay at the bottom of the lamp. But when it's heated, it will be a bit lighter than water, so it will rise. And if you have a bulb under this glass bottle that is continuously heating this wax, then the wax will go up and go down. So that's very good decoration. And how do we use this to create random numbers? Actually, in this pattern, they are using a digital camera that is continuously capturing this lava lamp. And by analyzing this captured picture, they create random numbers. So you can check this US pattern. That's the first kind of true random number generators. The second one is called quantum RNG. Let me show you a movie here. Okay, let me play. So there is a device, a gun, that's emitting photons. And here is a mirror. Sometimes the photon will pass the mirror, and sometimes the photon will be reflected by the mirror and go into the counter. And if it's reflected, it will be recorded as 1, otherwise it is recorded as 0. And then after you get a sequence of 0 and 1s, you can use them for whatever purpose you have. Let me show it to you again. Very quick. So this is a photon. Photon is the basic element of light. So here's the mirror. Then it gives 1. That's 0. And it's 1. And it's 1. So passage is 0. This is a physical device to create random numbers. And there are many other ways to create random numbers. But I just want to give you a sense that what true random number generators are. But another kind of random number generators are pseudo-random number generators, which are computer programs. And today we are going to focus on two of them. The first one is called linear congruential. The second one is called Mersenne twister. So the outline today is, first, the definition of pseudo-random generator I already introduced. Now I will talk about random sequence and varieties of pseudo-random generators and how it's used in traffic simulators. Okay. Now let's compare PRNG and TRNG. In terms of efficiency, pseudo-random generator is excellent because you are using a computer program, so you can generate a sequence of billions of numbers in a second. But if you use lava lamp, you probably will get only one number per second. So this is dramatically different. But in pseudo-random generator, the results are deterministic. But in PRNG, it's non-deterministic. And each pseudo-random generator has a period, so it's periodic. So if you generate a sequence that's long enough, you will find the sequences are actually repeating themselves. The period may be very long, but they all have a period. But true random number generators are aperiodic, so they don't have a period. And if we want to choose the most suitable generator in our applications, in simulation and modeling, I think it's enough to use pseudo-random number generators. But in the application of lotteries, gambling, or security, you probably use PRNG, right? And when we say we are using PRNG, it doesn't mean that we cannot use a computer to do that very fast. But you have to pre-compile a sequence before you have this application. So you can pre-compile a sequence that is very long before you use this application. Okay. Now I want to introduce the first concept of today that's very difficult to understand. Random sequence. So why is random sequence hard to understand? Let me give you an example. Let's suppose you are tossing a coin or flipping a coin for several times. And each coin has two sides, tail and head. And we use like 0 to indicate tail and use 1 to indicate head. And we toss it 23 times. We have two results. Which one can be called as random sequence? Anyone answer me? A and B. Which one is a random sequence? Looks like a random sequence. B, right? But why? Why is it more random?
Because there are not all zeros.
Right. But if you analyze the probability that you get A and your probability of getting B, they are equal. They are all equal to 1 over 2 to the power of 23. So why do you say this is more random? Because this is possible. This is also possible. You get this with the same probability of getting that. So that gives you a question. Why is it more random? The mathematicians could not answer that, but they turned to a more complex concept called infinite sequence. For finite sequence, I can just tell you, these two can both be from a random sequence. They are both, but let's consider infinite sequence, which is an infinite sequence of ones and zeros. Because according to the law of large numbers, we can capture some characteristics when the sequence grows very long. So the mathematicians are thinking about infinite sequences. There are some approaches to define this random sequence, with infinite size. The first one is called the measure theoretical approach. In this kind of approach, they are trying to use the law of large numbers, and they are trying to measure the result. Let me give you an example. As you said, like if you generate a very long sequence containing 0 and 1s, then according to the law of large number, the 1s should be of almost 50% probability. Right? So there should be 50% of 1s and 50% of zeros when the sequence is as long as it approaches infinity. But is that enough? And right here. So then I give you this random sequence: 1, 0, 1, 0, 1, 0, 1, 0. Then we have 50% ones, 50% zeros. Is this, if it is infinity and it's an infinite sequence, is it random? No. But why? So they had an idea that they want to define a function to extract a substring from this sequence. For example, if I define a function to get this string, get every odd digits, then the result will be 1, 1, 1, 1, 1. And this will not satisfy the 50% ratio. Understand that? So if I create a function to only get the first, third, fifth, and seventh, like these odd digits from this sequence, the result will be 100% 1. So that's why they said this is not random. And they want to define a random sequence that no matter how you select your function to extract the substring or the subsequence will always satisfy the law of large numbers, which means the result will always contain half zeros and half ones. So this is the basic idea of this measure theoretical approach. Clear? You don't need to fully understand that, but I just want to give you an overview of that approach. Actually, it's more complex than I said, because every approach will take you like several lectures to understand. The second approach is called the incompressibility approach. In these approaches, the mathematician wants to think about the problem in another way. So, I think all of you have used some compression software, like WinZip. So you have a large file, then you can compress it. You will become a smaller file. And the reason that you can compress your file is because your file has some kind of redundancy. Let me give you another example. So we have a sequence of 10, 10, 10, 10, 10. So 10 digits. And this can be seen as 5 1 zeros, right? 5 is 101 binary command. So actually, we only use 5 digits to represent this 10-digit sequence. So this sequence is compressed to another sequence. And the ratio of compression, let's assume it's a ratio compression. We use R to indicate the ratio of compression. And as the sequence grows as large as infinity, we assume, a mathematician assume that this ratio will never exceed the length of the sequence minus a constant. They first assume that. Suppose R is the compression ratio. Yes, the compression ratio, which means the new size minus the old size and something like that. And this ratio will never, let me define it another way. So originally it has a length of A, now it has the length of B after compression. Then R is defined